Welcome to The Explainer. Today we are going to tackle a huge topic, machine learning. And we're going on a bit of a journey, starting with something as simple as a line on a graph and ending up with technology that can literally monitor our entire planet from space.
So let's just jump right in. We'll kick things off with a classic question, right? Can we really use the past to predict the future? I mean, this whole idea, it's the beating heart of what machine learning is all about.
And to really get a feel for how this all works, we're going to start at square one, like the most basic form of machine learning you can imagine. We're just going to try to fit a simple, straight line to some data. You've probably heard of it. It's called linear regression.
Okay, so check this out. These are the winning times for the men's 100-meter sprint, going all the way back to 1980. And you can see it right away, can't you? There's a pattern. The times are, for the most part, getting faster. Yeah, there are a few little bumps here and there, but that overall trend, it's definitely headed down.
So what if we just draw a straight line right through those dots to kind of capture that trend? Well, now our super simple model can make a prediction. And get this, it spits out a winning time of 9.595 seconds for the 2012 London Olympics. I mean, wow, that is incredibly precise. But is that realistic?
Yeah, exactly. And the source material for this explainer really hits the nail on the head here. It says it's foolish to think you can predict something as chaotic as an Olympic final with a simple, straight line. And this really gets to a huge challenge in all of this. The real world, it's just not that neat and tidy. It's almost never a straight line.
So if a straight line is just too simple, what's next? We clearly need a better way to do this. And that means we got to get under the hood a little bit and figure out how a machine actually learns from data.
Now, when we talk about what these models do, it pretty much boils down to two main jobs. The first is regression. That's what we were just doing with the Olympic times, predicting a number on a continuous scale. The other big one is classification. That's when you're trying to put something in a box, a category. You know, is this an apple or a lemon? Is this email spam or not spam? That kind of thing.
Okay, so for a model to improve, it has to know when it's wrong and how wrong it is. That's where something called a loss function comes in. Think of it like a score in a video game, but where you want the lowest score possible. It's basically a formula that calculates how badly the model messed up. The whole point of training is just tweaking all its little internal knobs over and over again to make that loss score drop as low as it can possibly go.
So how does it find that lowest score? Well, it uses a process called gradient descent. The best way to think about this is to imagine you're standing on a big, hilly landscape in the fog, and you want to get to the very bottom of the valley. What would you do? You'd look down, find which way is steepest downhill, and take a step. Then you do it again and again. That's literally all gradient descent is doing, taking tiny steps in the steepest downhill direction of that loss score to find the absolute minimum.
And this whole process brings up a really critical balancing act. On one hand, you can make your model so complex that it basically just memorizes the data you showed it, including all the weird random noise. We call that overfitting. On the other hand, your model can be too simple, like our straight line, and completely miss the real pattern. That's underfitting. Finding that perfect sweet spot in between, that's the name of the game.
Okay, but what about when the patterns aren't just simple lines or curves? What if you're trying to do something really hard, like recognize a face in a photo or understand what someone's saying? This is where the whole field took a massive leap forward, thanks to neural networks.
And believe it or not, this whole idea starts way back in the 1950s with a thing called the perceptron. It's the absolute building block, designed to be like a single artificial neuron. It just takes in a few inputs, decides how important each one is, and then makes a simple yes or no decision. Should I fire or not? That's it, a tiny little decision maker.
But here's where the magic really kicks in. What happens if you take tons of these simple little units and stack them together in layers? It's like building with Legos. The first layer might learn to spot really simple things like a straight edge or a corner. The next layer takes those patterns and learns to combine them, maybe into a circle or a square. You keep stacking, and pretty soon, these deep networks can learn incredibly complex ideas all on their own.
Now, for something like an image, we use a special kind of network, a convolutional neural network, or CNN for short. And it's pretty clever. Instead of trying to look at the whole picture at once, which is just overwhelming, a CNN works more like our own vision. It scans the image in small chunks, using little filters to look for basic stuff, edges, textures, colors. Then, it pieces together what it finds in those little patches to recognize bigger objects. It's a much smarter way to see.
And this ability for networks to see and make sense of images, well, this has opened up a whole new world of possibilities.
especially in fields like the earth sciences, where scientists are just drowning in satellite photos and drone footage.
So, for instance, we can now use AI models to look at satellite images and figure out what crops are being grown where. The model just learns the unique visual signature of, say, corn versus wheat from space. And this lets us keep an eye on our global food supply in a way that was never possible before, pretty much in real time.
And the environmental applications are huge and frankly critical. These models can become digital first responders after a disaster, instantly mapping out all the flooded areas. They can be our planet's watchdogs, spotting illegal logging in remote forests. They can even act like atmospheric detectives, pinpointing pollution sources from orbit. It's really amazing stuff.
So this all sounds incredibly powerful and probably really complicated, right? But how do people actually build these things? Well, you might be surprised at just how accessible the tools of the trade have become.
Basically, the entire world of machine learning runs on just a handful of amazing open-source toolkits. You've got the big powerhouses like Google's TensorFlow and PyTorch from Meta. They do the heavy lifting. Then you have things like Keras, which is a user-friendly layer on top, and scikit-learn for all the classic stuff. It makes building these models so much faster.
And this is what blows my mind. Just look at this little chunk of code. That right there, that's a simple 2-layer neural network. That's it. It's pretty readable, isn't it? All the incredibly complex math, it's all handled for you, behind the curtain. This lets people focus on the big picture, on the design of the network.
But here's the most important part, the real game changer: access. It's been totally democratized. Tools like Google Colab mean that literally anyone with an internet connection can get their hands on massive computing power, including the special GPU hardware you need, for free. This has just unleashed a tidal wave of creativity and innovation all over the world.
So we've got the basic ideas, we've got the tools that anyone can use, but where is this all headed? What's coming next? Well, one of the wildest frontiers right now is generative AI. And a classic example here is something called a GAN. It's brilliant, really. You have two neural networks that are basically enemies. One is the generator. It's an artist trying to create fake images. The other is the discriminator. It's an art critic trying to spot the fakes. They go head-to-head, training each other until the artist gets so good that the critic can't tell the difference anymore.
And that incredible power to not just see the world, but to create new pieces of it, that brings us to the final and maybe the most important question of all. As these AI systems get better and better at modeling our reality, the big challenge isn't just about making them more accurate. It's about making them responsible. How do we ensure these powerful tools are built to reflect our best values? That's a conversation that's bigger than just code, and it's one we all need to be a part of.